Today is the final lecture of this semester. We will continue to talk about integer data structures. Last week we talked about why fast tries, and today we'll discuss another data structure which makes the same thing but has a different time complexity. We'll talk about fusion trees. So what is a fusion tree? A fusion tree is another data structure which is used for integers and actually do the same thing as a binary search tree. So again, we have a set of integers and we want to make operations like insert integer, like remove integer. And okay, let's do it like last week. We'll make a operation lower bound. So again, it's like in C++ lower bound in set. So you need to find the closest integer to this x. So we'll find the minimal y such that y is greater or equal than x. And last week, again, let's repeat. Last week we discussed the data structure called y-fast trees. And these y-fast trees make all these operations, and time complexity is y-fast try. So in y-fast try we make all this operation in log w operations. Also, you can use binary search trees. If you use just regular binary search trees, you can make all these operations and time complexity will be log n, right? So when w is less than n, actually it's more efficient to use y-fast tries or maybe Van-em-de-Bos trees. We didn't discuss Van-em-de-Bos trees, but it has same time complexity. So you use Van-em-de-Bos trees or y-fast tries if your w is small. And again, w is the size of the words in your computational model. So in your computational model, you work with integers, and the size of this integer is w. I just repeated, we discussed it last week. Today we discuss one more data structure. It has all the same operations, but different time complexity. Time complexity of the data structure we'll discuss today will be fusion trees. Will be something like, not exactly, but close to w of n. So what's interesting about this? The interesting about this is that in y-fast tries or in Van-em-de-Bos trees, the complexity actually increasing when you increase the size of the word. So if you make longer integers, the time complexity is increasing, yeah, because this log w is increasing. Here, the time complexity is actually decreasing. So if you have bigger integers, your data structure actually works faster. That's kind of interesting. And why can it be possible? Why can we get a fast data structure when we increase the size of the integer? It's basically because we allow to make all the arithmetic operations in constant time. So we have these long integers, and we allow to make all the operations in constant time. All operations like you can make sum, you can make multiplication, and so on. So all the standard arithmetic operations work in constant time. Again, the most strange thing is that we can multiply integers in constant time. So we will allow to calculate the multiplication of two long integers in constant time. This is a big assumption that we can multiply two long integers in constant time. We still don't know how to do it. So we don't know how to build the long integers with fast multiplication. But if we allow to make long, usually when you think about RAM model, you think of you assume that you can multiply integers in constant time, and these data structures are all about this. If you assume that you can make arithmetic operations in constant time, then you can make these operations. And again, if you multiply long integers in constant time, you kind of make a lot of things in constant time. So if you make long integer, then you multiply, you make many small operations in a single operation. Yeah. So you multiply all pairs of bits in constant time. And if you have longer integer, you have bigger number of operations performing in constant time. So it's actually, this is why this time complexity will be decreasing. So we have like more parallelism in this. When you increase the size of the word, you will have more parallel operations. So time complexity will be decreasing. That's the idea. Okay. Okay, let's go. So what's the idea? The idea is to make a search tree, but not binary search tree, but something like this. So we'll make a search tree, but in this search tree we'll make not 2 children, but many children. So let's have, in each node, let's have b children, like in B tree, right? And so on. And so on. So every node has exactly b children, not exactly b children. You can, so if you want to make insertions and removals from this tree, you actually need to have some gap between minimal and small maximum, but that doesn't matter. Actually, what you need to do is make a b tree, right? We discussed b trees last year, but it's not that interesting, so it's not lecture for today. But you need to make a b tree. So you need to make a tree where each node has about b children. So in b tree you have some gap. So the number of children is between like b over 4 to b. So you can balance this tree. Not important today. Let's say that each node has b children. Now we need to find the value of b. So the height of this tree is, so I want the height of this tree be big O of log W of n. So what value of b should I pick? Any ideas? Again, if it's your first time here, you need to say something in the chat at least every minute. Okay? So I understand you're here, you understand what's going on, and so on. Okay, so b is like a branching factor. So in each node we have b branches. I want to pick a value of b such that the height of this tree is big O of logarithm base W of n. Yes, every minute just say something. If you don't know what to say, just say something. If I'm asking a question, better to try to guess the answer. Again, b is a branching factor. Yeah, each node has b children. So, if each node has a b children, what will be the height of this tree? The height of this tree will obviously be log n base b, right? And I want to pick a value of b such that this height is actually a big O of log n base w. So the question is, what is b? Okay. Not a hard question, right? Any ideas? I will wait. Just say something. B equal to W is good guess. Okay. B equal to W will obviously give you this complexity, but unfortunately, it's not possible to, no, it's possible, but not exactly, to build a tree with this branching factor. So I need to make a small branching factor. Yeah, it's actually also works, but yeah. N power log Wn is the same thing. Yeah, so I need B to be n power lambda. So, but if you put n in the power of log, it will give you W. Not exactly. No. Okay, like this back. Doesn't matter. So, yeah. So B equal W will be good, but unfortunately we will not be able to make this large branching factor. So we will actually build small branching factor. The branching factor will be W. So if you pick B as W in any power, you will still have this time complexity, because log Bn will be log n over log B, right? So if B is W power n, then this is log n, this is alpha log W, so it's 1 over alpha log Wn, right? So, so you can pick for B not W, but W in any power, and it will work. And in our solution, we will pick B as, spoiler alert, we'll make B as W in power 1 over 5. So the branching factor will not be W, but it will be big enough to make the height of the tree big O of logarithm base W. Let's stop here for a moment. So why this structure is not very practical? Because let's see, if we want to make branching factors, for example, let's move here. If the branching factor is, for example, 4, if it is less than 4, we can implement it without all the stuff. Yeah. So to make this structure at least somewhat effective, we need to have branching factor of this 4. If your branching factor is 2, you can make a binary search tree, right? So if branching factor is at least 4, then W should be like 4 power 5, so it's 124. So we need 1024 bit integers to make branching factor 4. So even the slightest attempt to make this structure effective is only possible when you have these huge integers. So the size of, again, W is the size in bits of all the integers. Like in modern processors, we have like 64 bits integers or 128-bit integers. We don't have usually the machines with 1024-bit integers. Yeah, so it's kind of hard to implement. But to make this structure work, we actually need to have integers of size at least 124 bits. If you want to make this structure even more effective, for example, if you want to have branching factor of 10, so that's something interesting, right? So if you have 2 children or 4 children, that's not a big deal. But if you have 10 children, that may be something interesting. But if you want to have branching factor 10, then the size of the integers should be 10 power 5. So you need to have 100,000 bits in each of your integers. We don't know how to make such big integers and still have multiplication constant time. So not very practical data structure, but in theory it's cool, right? So again, in theory, all these data structures are about what to do when you have big integers. So if at some point we will manage to build a machine which has very big integers and it can calculate all the arithmetic operations in constant time, then we can do very cool stuff. Okay. What's the idea? Again, we'll pick this branching factor. And in each node, we'll have b children. So how to have b children in a search tree? Well, in binary search tree, again, in the binary search tree, you have a single key. Again, what happens in binary search tree? You have a key x. Here you have all elements less than x. Here you have element greater than x, right? That's how binary search tree works. If you have b children, for example, if you have, let's say you have 4 children. So you have the node, and it has 4 children. You need to split all the segment of possible integers into 4 segments, right? So here you have all elements less than x1, here greater than x1 but less than x2, here greater than x2 but less than x3, and here have a greater than x3. So you need 3 keys here. So you need, in each node you have 3 keys. And when you step into this node, you need to, so again, what happens? You find the lower bound of x. So you move to this node in your recursion. Let's look how, it's the same like in binary search tree, but now you have b children instead of 2 children, right? So you have value x, and you need to find out in which of these subtrees the value x should belong, yeah? So what you need to do, you need to find the segment which contains your value x, right? So how you do it? No, you basically need to make a lower bound in this set of integers. So you have this set of keys inside your node, and you need to calculate lower bound for this incoming value x. Yeah? So you have this value x, you calculate lower bound of these elements for the value x, and then you find out which segment actually contains your element x. Then you go to this subtree and so on. So again, you start from the root with some value x. You want to calculate lower bound. So you have b children. You need to find out which child actually contains value x. So you calculate lower bound of the keys inside this node, select one of the children. Now go here. Again, you have b children. You need to select one of the children and go to this subtree. So you calculate lower bound inside this node, select one of the children and go to this node and so on. So each time you have b children and you need to select one of them and to go there in your cursor, right? So now the only thing you need to make is to calculate lower bound in this small set of b integers. So now the problem we're solving is the following. We have the node. Inside the node we have b keys. So x1, x2, and so on, xb. Actually b minus 1, but doesn't matter, so plus minus 1. I will omit all the constants unnecessary, right? So we have node. In the node we have b keys. And we need to calculate lower bound for incoming value x inside this node. So we will, when we calculate lower bound inside the node, we will select one of the children, then go there and do the same thing recursively. So the depth of this recursion will be the height of this tree. The height of this tree is log base W. So now we'll solve the following problem. We have b values, and we need to calculate lower bound inside these b values in constant time. If we will manage to do it in constant time, then each time we go to some node, we calculate the lower bound in constant time, select the child, go there, again calculate lower bound in constant time, select one of the children, go there, and so on. So time complexity will be the height of this tree. The height of this tree is log base W. You forgot to say something. Say something. I just need to see your life here. Okay. if everything is clear, just say everything is clear. Okay, that's now let's move to this problem. So here we need to calculate lower bound in this small set of integers. Oh, let's say, for example, let's say W is, let's say, 8 and B is, well, it must be W in power 1 per 5, but it will be too small. Let's just to show you what's going on, I will pick, usually I will try to pick B as W power 1 over 5, but if you put 8 in power 1 over 5, you will have less than 2, it's not good. So let's say B equal to, let's say 4. Again, just for example. That's not usually the values you need to pick, but again, to make all this thing work, you actually need big value of W. But I will not try to write the 1024-bit integers here. So let's have some 4 integers. Let's have something. Let's have 0, 0, 0, 1, 1, 0, 0, 1. Okay, that's the first one. Okay, let's use different letter here. Let's say A1. Because I will have X later, so. So A2 will be, let's say 0, 1, 0, 1, 1, 0, 0, 1. Why not? That's too boring. Let's make 0 here and 1 here. Yeah, good enough. Now the third one, let's say 1, 0. Okay, let's make this. Okay. It's usually hard to make a good example. 0, 1, 1, 0, 0, 0, and A4, something like this. Yeah. I don't like it. Let's make this one. Yeah, good enough. Good enough. So again, we have B integers, and the size of this integer is W. What we'll do, we will build a B trie like in previous lecture. So let's try to build a trie from these integers. Again. Okay, let's make a compressed trie, like in suffix tree, right? So here we have 0. So here we have 0, 0. Here to the left we have 0, 1, 1, 0, 0, 1. To the right we have 1, 0, 1, 1, 0, 1. And to the right we have 1, 0, 1. And here we have, oh no, it's, I hate it. I want them to have to be in increasing order. Okay, and here we have 0, 1, 0, 0, 0, and to the right we have 0, 1, 1, 1, 1. Yeah. like this. So that's a compressed try of these integers, right? So if you represent these integers as strings and try to build a try of these strings, you will have something like this. Now, what will happen if I want to find something in this try? So, for example, you're given some integer, you want to find this integer in this try. What you will do? You will start from the root and then follow the path each time you compare your digit and the digit in your try. And then follow this path from the root to the leaf of your tree. Right? That's how the tries work. Now let's see. The only important spots in this try are the spots when you have two branches. So this is important spot. Here you actually need to select which way to go. And here's important spot. You need to select which way to go. And here's important spot. So when you follow some path in this try, you actually have choice only in these points. These points, in these points you check one of the bits of your integer. So let's mark these bits. So we have only 3 important bits in your integer. So important bits are the bits when you need to choose your way. So you need to go to the left or to the right. So you make this what you make? You make this choice in 3 points: here, here, and here. So when you're standing here, you look at the first bit of the integer. So the first bit is interesting. Again, this bit is interesting. Yeah. Here at this point, you look at the third bit, right? So you already know you have 0, 0, and you look at the third bit of the integer. So the third bit is also interesting. Let's mark. So this bit is interesting. And here you look at the fourth bit. So the fourth bit is also interesting. So these 3 bits are interesting bits. Now, how many interesting bits you have? That's a question you need to answer. Again, we have interesting bit when we have something like this. So we have two branches. So in some node we have both children. We can go to the left or we can go to the right. So the number of interesting bits is no more than the number of these interesting points. So how many interesting points you may have in your try if you have b values? So the number of values here is b. Yeah. So the number of interesting points is at most b minus 1. So you have at most b minus 1 interesting bits. I'll say b just for simplicity. I will omit all the non-important constants here. So we have no more than b interesting bits. Yeah. Now, what we'll do? We'll make what's called a sketch of each integer. So for each integer, we will make a sketch. This sketch will contain only interesting bits of this integer. So let's put it here. So a1 prime, a2 prime, a3 prime, a4 prime. So we take the first integer and select only interesting bits. So here we have 0, 0, 1. For the second integer we have 0, 1, 0. For the third one we have 1, 1, 0. And here we have 1, 1, 1. So again, you have array of big integers. Each integer has W bits. You make the following: you select only interesting bits in each integer, and then construct the sketch of this integer. This sketch contains all important bits of the integer. So it's actually, again, these bits are enough to distinguish these integers from one from each other. So when for example, these sketches are always sorted. Yeah? Because again, the first bit is interesting, so it will be presented in this sketch. So first we have all integers with zeros, then we have all integers with 1, and so on. If you look at the difference between two consecutive integers here, then the bit when we differ is actually important bit. So, for example, first and second integer have different third bit. Second and third have different first bit, and these two integers have different fourth bit. So if two consecutive integers are different in one bit, this bit will be important. So it will be presented in the sketch, so the sketches will be sorted. Good. Now, how to calculate lower bound? To calculate lower bound, we will do the same thing at the value of x. So for example, you're looking for some value x. Oh, no, let's say something. Let's say 0, 0, 1, 1, 1, 0, 1, 1. So you have some value of x. And you want to find this value in your trie. Again, like in previous lecture, what we're doing to find the value, we will follow the maximal prefix of x in the trie. And find the position when we actually go away from this path. For example, if you try to look for this value in this trie, you follow the path. So you start from the root. You have 0, 0, then you have 1, 1, 1, and so on. So you have 1, here you have 1. So you stop at this position, and in this position you actually try to go to the right. So in the trie, your path goes to the left, so you have 0. The next bit is 0. But your x is trying to go to the right. That's what you need to find. So you need to find the positions 0, 0, and so on. So this will be the maximal prefix of x, which actually represents in your trie. Again, we discussed it last week. It's the same thing. So to find the lower bound, we need to find the position when we go away from the trie. So we'll find the maximal prefix of x, which is presented in our trie, and then find the direction when we move. So here we stop at this position and move to the right. If we know the position and we know which way we move, we can find the next the lower bound. Again, the same thing like last week, but the idea of how to find this maximal prefix is slightly different. Is it clear enough? You're too quiet. It's always nervous when you are quiet. So again, last week we discussed the Y-first trie, and we kind of make the same thing. We try to find the maximal prefix of x, which is presented in the trie. If we know the maximal prefix, then we know that our x going like here and then move to the right. So it's easy to find the next position in the trie. So we just follow this, follow the next tree, find the maximal here, go to the next, and so on. Do the same thing. Yes, lower bound is minimal wise, greater equality. No. Yeah. It's like in C++ lower bound. Usually it's called different in papers, but just to make it close to the reality. So in C++ set, it's called lower bound. Not big difference. So, so again, if we find this maximal prefix, then we're actually done. So we know that we follow this path, then go to the right. This information is enough to find the lower bound. Now, how to find this maximal prefix? We will use these sketches. So first we will build a sketch from this x. So from this x, we will find all these important bits. So we have first, third, and fourth bit are important bits. So we'll construct the sketch of x. The same technique. So we'll say it 0 x prime, 1 1. Now we need to find for this sketch the sketch from this list, which has a maximal common prefix with x. So we'll find this. This is the maximal prefix because it's here. So how to do it? So you have sketch of x. You have list of sketches. And you need to find the maximal prefix of x, which is common to some of these sketches. How to do it? We need to do it in constant time, right? So we need to, in constant time, to find this value 2, like 2. So we need to say that there are 2 bits common in these 2 sketches. How to do it in constant time? The same trick like in previous lecture. So all these sketches are very short. So the size of all these sketches is b. And b is about, I will empower 1 over 5. Let's see exactly. Just for simplicity. So what we can do, we can put all these sketches into a single word. So if you just take all these sketches, put them in a single word, it will fit in one word. So you will make one word. Sorry, I'm out of space here. So we'll put A1 here, A2 here, A3 here, A4 here. Prime, 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 prime. So we'll make a single word containing all the sketches. And then in this big integer, we need to calculate something like lower bound again. We can calculate lower bound using the same technique we discussed in the previous lecture. So again, you take your x prime, you build something like this. So you build x prime, multiply it 4 times, like this. Then you subtract one from another, you get this array of booleans, you make the sum of all these booleans using, again, the same technique like in previous lecture. And you will find the lower bound of this x prime inside this small array. So again, since the size of all these integers is small and the number of integers is small, so you have small number of small integers, you can fit all these small integers into one big integer. And then using all these operations, again, you can calculate operations on big integers in constant time. So you just put all small integers in one big integer, and then you calculate all these operations in constant time. So in constant time, you can find the lower bound of this x prime inside this set. And when you calculate lower bound, it's easy to find the maximal common prefix. The maximal common prefix will be something like one of the 2 neighboring elements. So you know that your lower bound is here. So your x prime must be here. So one of these neighboring elements have the maximal common prefix. Is it clear enough? Once again. So I have this number x. I want to find the maximal prefix, maximal common prefix of my x and one of the integers in this set. So before I do this, I calculate the sketch of x, this small integer, and then find the maximal sketch which have maximal common prefix. So instead of working with these big integers, I work with these small integers. For this small integer, I need to find the maximal prefix which is common to one of these small integers. I can do it in constant times because this size is small. So I can fit all these integers into one big word like this. And then I can calculate lower bound on constant time. Again, the same trick as we did last lecture. So we put all these integers into single word, then subtract this from this. We'll have array of booleans for each integer. We know if it is smaller or not. And then we just need to have sum of all these booleans using the same trick as last lecture. Okay, hope it's clear enough. Now we know now we found this sketch. So we found this sketch with maximal common prefix. What we'll do next? We will take the whole number corresponding to this sketch. So we take this number. And for this number, we will simply calculate the longest common prefix. So we will calculate longest common prefix of this number A2 and this number X. It will be 3. That's all. That's all. Okay, once again. I have number X and the list of integers. I want to calculate the longest prefix of X, which is also a prefix of one of these integers. If I know this common prefix, then I can calculate lower bound. Because again, what happens? I have this trie. I will go from the root to this position when I'm trying to find X, and then go away from this trie. If I know the position where I go away from the trie, I know the lower bound, because I know if I go away from this position to the right, this will be the next element in my array, right? So I can pre-calculate all this stuff, and it's actually not that hard. So if I know the position when I left the trie, I actually can pre-calculate the lower bound. So that's all I need. So how to calculate the maximal prefix of X, which is common to some of these integers? I will calculate sketches of all these integers. So I leave only important bits. So I calculate this array of small integers, and then I calculate sketch of X. So I have array of small integers here and small integer X. Then I calculate lower bound of this small integer in this array of small integers, and find the integer with maximal common prefix. So this X prime and this A2 prime has big common prefix. Now I take this X and A2. So I put back all removed bits. So I have this long integer here and long integer X. And then calculate the maximal common prefix of X and A2. And it will give me the maximal common prefix. Why it is correct? Why it's correct? Because if you try to follow the path from X, from the root, using the bits of X, you will make all the same choices in all important bits. So if you look at the integer X and integer A2, and try to follow the path from the root using these bits of X and bits of A2, then in all these junctions you will have the same choice, yeah? Because all the important bits are the same. So you have bits in X and bits in A2. All first important bits are the same. So in all junctions you have the same choice. But yeah, that's all. Yeah, that's all. So if you leave the trie at some point, you will leave it at a point when you have different bit of X and A2. So the first different bit is actually the bit when you leave the trie. Yeah, that's very nice, but you better answer the question. It will be much more productive. Go. That's all. Yeah, by the way, how to calculate the maximal common prefix? So if you have two integers, how to calculate the maximal common prefix? I didn't mention this. Let's put it here in the corner. So if I have integer a and integer b. Sorry. How can I calculate the maximal common prefix in constant time? Well, let's put some bits there. So you have two integers. You have some bits, let's say 0, 1, 1, 0, 0. And here we have something 0, 1. So here's a common prefix. Yeah. So how to find the length of the common prefix of two integers? No? It's actually quite easy. You just calculate the XOR of these two integers. So you calculate A XOR B. So all these bits here will be zeros, and the first important bit will be 1. So you just need to find, So you just need to find the highest bit in the XOR of these two integers. So you calculate the XOR, then find the highest bit. In the previous lecture, we discussed how to find the highest bit in constant time. So you apply all the same technique to find the highest bit in constant time. Then you will find the LCP of two integers in constant time. Thanks. It's good to have you back. Okay. Now, that's all. So again, the full algorithm, how to do it. You have the list of big integers and one big integer x. You need to find lowest common prefix of x and one of these integers here. You do it like this. You find all important bits here. Calculate these sketches. Calculate sketch of x. Sketch is just the integer which contains only important bits. So leave only these important bits. Build this, and so on. Now you find the lowest common prefix of this sketch and one of the sketches from your list. This will give you the closest integer in your set. Now you go back to this integer, so integer which corresponds to this sketch, and calculate LCP of this x and this integer. And this will give you the length of LCP. And again, if you know the value of LCP, you know what will be the lower bound. That's all. There's only one thing left, actually. Just one small detail of this algorithm is actually not discussed. Okay, can you spot it? So basically, all elements are pretty simple. Here you need to calculate the highest bit. Here you need to calculate the lower bound inside a small array of small integers. You can do it like we discussed in the previous lecture. The only thing we need to discuss is actually how to build the sketches. That's not trivial. So what you need to do, you have a long integer and you have some important bits. So you have a list of important bits. Oh, I put it here. a little bit shorter, it's too big. So you have a long integer a, and you have a list of important bits. So you have like positions here, 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 and here. Let's see, positions b1, b2, b3, and b4. And you need somehow to construct the sketch of this integer. So you need to make integer a prime, which contains only integers a1, a2, a3, and a4. a4. That's not easy. So if you think about it a little, so what's the problem here? The problem here is that you can remove all other bits. That's not that's easy. So you can just end your integer with some mask which only contains these bits. So all other bits will be 0. So let's just say all other bits are 0. So here all bits are zeros. Yeah. You want to kind of shift these bits to the same positions here, but again, what's the problem? You have all these bits, but they are far from each other, and I want to move them closer to each other. So I want to move them in these 4 positions. Yeah, and I want to do it in constant time. So in constant time, I want to move all these separated 4 bits into this small window. How to do it? So if you remember if you remember the previous lecture, not divide, you can multiply it. Yeah. No, you can use division. You need to. In last lecture we did kind of the same trick. We had few separated bits and we put them together using multiplication. So we multiplied by special mask, and this special mask just, again, what is multiplication by a mask? You shift and add, shift and add, shift and add. And it's the multiplication by the mask is basically the sum of your integer shifted to these positions. We'll do the same trick here. But the difference is that in that problem we discussed last week, we have the distance between these bits was even. It's awesome. Yeah. Last week we discussed almost the same problem. We had different bits, but the distance between these bits was the same. So this distance was always b. Yep. So when distance is the same, we can shift it to b minus 1 elements, add, shift to b minus 1, add, shift to b minus 1, add, and we can do it in one multiplication. Here, the distance between these bits is different, so it's kind of more complicated. But we can still apply the same trick, but slightly modified. So what we'll do? A by some mask again. So we'll multiply m by some m. M will be just a mask of zeros and ones. So we have ones in some positions. M1, M2, M3, and M4. So if I multiply A by this value M, what will I have in the result? In the result, I'll have a big vector when this A1 will move to positions B1 plus, so I have 4 elements equal to A1. in positions B1 plus M1, B1 plus M2, B1 plus M3, and B1 plus M4, right? So for each bit, I will have 4 copies of this element, no, B copies of this element. If I have B bits, I have B bits here, so number of bits will be equal to B. So we have B bits here, B bits here. So for each bit, I will have B copies of this bit in these positions. Now, what I want to do. First of all, I have many copies of each bit. If I have these copies in the same position, they will it will be something I don't want to deal with. So I want these bits be in different positions. So I don't have deal with you have sum of 2 ones and have 0 in this position and so on. So again, if you put the bits in the same position, they will sum up and make something strange to the previous bit. I don't want to deal with this. So I want all these positions to be different. So I want all positions Bi plus Mj be different. Now, the positions I will use for my sketch are positions Bi plus Mi. So positions Bi plus Mi will be the positions I use for my sketch. And I want these positions to be increasing. So in the final sketch, I have my bits in the same order. And finally, I want all these positions for my sketch fit into some small window. So I want to be in some window from L to R, such that R minus L is no more than B in power 4, like this. That's why I have B as W in power 1 over 5. So I can fit this number of B sketches. Actually, the size of the sketch will not be B. Size of the sketch will be B power 4. But still, if the size of the sketch is B power 4, I can fit B sketches into single word. How will I achieve this? I will achieve this using a very simple trick. I will say that Bi plus Mi actually should belong to the window from W plus IB third. Yeah. To W plus I plus 1. Should be minus 1 somewhere. Let's say minus 1. So again, AM will look like this. Yes, I enumerate bits from left to right. That's not convenient, but usually you enumerate bits from right to left. But I enumerate all arrays from left to right, so I enumerate the bits from left to right. So here's the least important bit, here's the most important bit. So I will put them here. Here. I will make 4 groups. So bit A1 will be put here, bit A2 will be put here, bit A3 will be here. So size of each group is B So the size of this sketch will be B4. Yeah. That's all. That's the whole plan. Now, I claim that it's always possible to pick values m such that these constraints hold. So how can we pick the values of m? Let's just pick them one by one. So we pick value m1 equal to something, m2 equal to something, and so on. Let's try to pick value mi. How can we pick value mi? We'll just brute force all the possible values of m and check that this constraint actually is satisfied. So actually, this thing will give us both these things, right? So they will be increasing because they belong to different segments, and they always belong to a segment. So we only need to take care of this thing. So we need to take care of all these sums will be must be different. So let's see. Let's try to pick value mi. So how to pick value mi? No. So what? So we need to have bi plus mi belong to this segment. Not to some segment. Okay, w plus e b3. 2w plus I plus 1 plus 1 b3. So there are b cube possible values. Yeah. So if I want this sum to be inside this segment, I have b square, b cube possible values of m, right? Now, some of these values cannot be used because they will not satisfy this constraint. So I cannot use value if some of these sums will be the same. So how many values I actually cannot be used? So for all previous elements here, see here I have I minus 1 elements. These I minus 1 elements actually generates I minus 1 square bits. So there are I minus 1 busy positions, so occupied positions, yeah? So again, I put I minus 1 bits here, I multiply this I minus 1 bits by this I minus 1 bits, so I have I minus 1 square bits occupied. I cannot use these cells anymore. Now, if I put some value mi, this value mi will generate I minus 1 values here. So each value of mi will generate I possible bad positions. And I don't want these positions to interfere with these occupied positions. So since every value calculate I positions, then I have something like this. So this is the total number of positions I cannot use for my mi. How to call them? Let's call them band values. Band is it 2n? I see that. And so you see that this number is actually less than b cube. Since I is less than b, so there are b cube possible positions, possible values for m. Some of them cannot be used because if you use this value of m, we have some of these sums will put the bits into the same position. So this is the maximal number of these unusable values. So we have this number of total values and smaller number of unusable values. So there is at least one possible value for mi. Again, we don't need to pick it fast. We can do it slow. We can just check all possible values of m, find the good value, then move to the next one. Again, check all possible values, find good one, and so on. It's slow, but it still can be done. Okay, that's all. That's all. So again, how you build sketch? When you need to have sketch of this long integer a, you just take your integer a, multiply it by this pre-calculated mask m. Have something like this. Now you have your bits in these windows. You just, again, you apply another mask, which only removes all bits except these bits you need. And then you have this sketch of size b power 4. b power 4 is enough, so it's small enough, so you can fit b sketches into a single word. That's all we need. Nice. Okay. That's all. So now we can calculate sketches. So we can in each node we can pre-calculate all this stuff and be able to find the lower bound inside the node in constant time. So time complexity for the lower bound will be log base w of n. Yeah. Unfortunately, for insertions and removals, it's slightly different. Because when you insert or remove, if you want to have the dynamic data structure, you need to construct this structure in some good time, yeah? But we need some time to construct all this stuff. So we need some time to, inside each node, we need time to sort all this element, to find all these important bits, to pre-calculate this mask and so on. And this actually takes time. And for example, here it takes something like b power 4. So if you want to insert or remove element, then your time complexity will be actually multiplied by b in power of, let's say, 4. Let's say log b, just to make it. And here also. So what we can do? What we can do to remove this b power 4 from time complexity? We can do the following. We can do the same trick like we did last time. So we can split all elements into groups of size again, you have all your elements, yeah? You split them into groups of size b power 4. And apply the same technique like in B trees. So when the block is too big, you split the block. When the block is too small, you merge the blocks and so on. So again, that's the same trick. Now, how to make operations? First, you find the lower bound to find the corresponding block, and then you need to find your element inside the block. To find the element inside the block, you simply use the binary search trees. So inside each block, you have a simple binary search tree. So your time complexity will be log n plus log b. It's log b power 4, but log of b power 4 is the same as log b. Right? So it's 4 log b. Right? And here will be plus log b. Like this. Cool. And the final moment. Now let's try to use both these techniques. So again, let's write it here. Now we have two techniques. We have Y first tries from the previous lecture, which works in log W, and we have this fusion tree with time complexity log B plus log Bn. Let's try to merge them. Again, okay, let's start from the form. So if this is log base n W, so if you have these two data structures, again, if you increase the value of W, this time complexity is increasing, this time complexity is decreasing. So when you have your values of n and W, you can select one of these data structure and use it. What will be the worst time complexity? So imagine you have your data structure. You have some number of elements, right? So you have n elements. Okay. And you have these two data structures. So if you increase the value of W, then the time of this data structure will be increasing. Not exactly like this, but okay. This is not logarithm, but okay. This will be y first 3. And time complexity of this will be decreasing. Something like, okay, not exactly like this, and not below 0, definitely not below 0. Something like this. So let's find this point. Okay, this function doesn't look like this, but close enough. One is increasing, one is decreasing. Doesn't matter. Okay. So let's find this point. So this point is when you choose one structure or another. So if you choose the optimal data structure, you will have time complexity like this, right? Because you know the value of W, you can select one of these data structures and use it. Yeah. So in both cases, you have time complexity like this. So this will be the worst possible point. What will be the worst possible point? Worst possible point is when you have the same time complexity. So this point is when log W is the same as log base W of n. Now, what is the value of W? It's easy to see. So log W of n is just log n divided by log W, right? So you just move this to the left, and you see that log W is actually the log n square root. So in this point, again, this is the worst possible value of W for the given size of the input. Okay? So in the worst possible case, log W will be square root of log n. So the time complexity of both these data structures will be square root of log n. What does it mean? It means for all possible values of W, you can build data structure with time complexity. Let's put it here. So for n, we can build the data structure with time complexity square root of log n. Oh. Now let's deal with this B. It's actually not that hard. So actually we have not log base W but log B. Again, let's make it clear. So again, you have value of n and W, and you want to choose one of these data structure. So if W, let's say if log W is less than square root of log n, then you use y fast trees or one of the both trees actually. No, V small e is big. Yeah. So you use y first tries or one in the boss tree. If you use y first try or one in the boss tree time complexity will be log W. Log W is less than the square, so it will be big O of square root of log n. Now, if log W is greater than the square root of log n, then you use fusion tree. And now let's find the optimal value of B. So I need, again, here, time complexity of fusion tree is actually like this. So let's find the optimal value of B. What will be the optimal value of B? And again, to find the optimal value of B, I need to find the value which gives me the same values here and here. So I want to have log B equal to log Bn. So B must be about, again, it's the same. So log B must be square root of log n. But I also need to B be less than 1.5, like this, right? Yeah, nice. So if I make B, let's say, no, I want to make B 2 power square root of log n, right? Let's make it like this. Yeah. So if you pick this value for B, then logarithm of B will be square root of log n divided by 5. It's good enough. It will give you the time complexity you need. And B will be less than W power 1 over 5 because, again, that's square root of log n is less than log W, so this thing will be less than 2 in power log W over 5. So it is W power 1 over 5. Yeah, good enough, it's working. So again, what you do, if your logarithm of W is greater than square root of log n, then you pick value B as 2 in the power square root of log n divided by 5. Nice value. And then use this value of B as a branching factor in your fusion tree. So the time complexity will be log B plus log Bn. Log B is logarithm of this value. So logarithm of this value is again square root of log n over 5. Logarithm base B of n, again it will be log plus log n divided by log B. Log B again is square root of log n divided by 5. Like this. So again, for all possible values of W, time complexity will be a square root of log n. Why is it interesting? Because again, we have a data structure with time complexity. Time complexity does not depend on this size of the word. So for all possible size of integers, we can build data structure with time complexity less than log n. And again, we just built a binary search tree. No, not binary search tree, but data structure with the same operations as binary search tree, with time complexity less than in binary search tree. And like we proved for abstract objects, we just proved that it's impossible to build data structure which works faster than log n time. But here, if we have integers and we can make operations with integers in constant time, we can actually build a binary search tree with time complexity less than log n. So the square root of log n. That's an interesting result, right? For example, you can use this structure to make a sorting algorithm. So you can sort integers faster than in n log n time. It's magic. Or you can make heaps or anything else. So binary search tree is basically does all the things. So you can make sorting, you can make priority queues and stuff. That's not the best result people know. People actually know how to sort integers in time n square root of log n. So that's the best known result by now for sorting integers. So if you apply even more complicated stuff, so they use quite crazy techniques when they try to build such algorithms. But if you apply even more sophisticated algorithms, you can build sorting algorithm for integers which works in n square root of log n time. It's open question if it's possible to sort integers in linear time. Nobody knows, but it looks like you might be able. No one knows how. Okay. So that's all for this semester. Okay. See you in February.